for quarks and gluons that are weakly coupled, that are almost free. And to do this, what we have to do is to try to prove this quark-gluon plasma at different scales, from the longest length scales, where we see the liquid behavior, to the shortest length scale, where we should find the quarks and gluons behaving as almost free. And for that, of course, what we do in particle physics is to try to look at different resolutions scales, and usually what we do in this kind of context is to do a deep inelastic scattering experiment to try to change the resolution. But we cannot do that with the QGP, because the QGP lifetime is very short, it lasts like 10 Fermi. So what we have to do is to try to prove the QGP using probes that are produced concurrently with the QGP. We cannot just send external probe to the QGP. Unfortunately, happily with these collisions, we produce also very high energetic particles that form what we call jets. So we can use jets that are produced with the QGP to try to prove the QGP at different scales, because jets are multi-scale objects. And that's basically my main field of research, and it's also a very active area of research in LEAP, and this is what we are going to talk about during the rest of this talk. So please, if you get lost or something, just interrupt me. So the idea is that we collide nuclei, and with these collisions, we also produce hard scatterings where there is a large transfer of transverse momentum, and in these large scatterings, you can produce highly energetic jets. So here we will have like a proton-proton collision where you produce back-to-back jets. And these jets in heavy ion collisions propagate through the quark-gluon plasma. And that means that as the jets are formed by quarks or gluons, they interact through the strong interaction with the quark-gluon plasma. And through these interactions, we can prove the quark-gluon plasma. And the idea is that jets are very useful probes because they are produced with the collision and they are highly energetic. And in principle, by measuring in the LHC differences in the jets' properties in heavy ion collisions with respect to PP, we can study the quark-gluon plasma because these differences are due to the interactions of the jets with the quark-gluon plasma. And these jets are produced at very high energies, and they have a range of, they are formed for several particles which have a very broad range of momentum and special scales. And the idea is that we can try to use these different scales that the jets prove to try to prove the different scales of the quark-gluon plasma and try to be sensitive to different properties at different scales of the quark-gluon plasma. So jets has been very useful in heavy ion physics. This is not something new. And the first observation of this phenomena that jets get modified when they propagate through the quark-gluon plasma, and the phenomena that we call jet quenching, was already obtained more than 20 years ago, apparently, in RHIC. And in this collider, they collide nuclei of lead, producing a quark-gluon plasma, and they measure back-to-back jets. So here we will have, in blue, in the stars, a jet at 0 degrees in azimuth angle, and what we see is that the jet at pi is basically very suppressed with respect to what we will see in proton-proton collisions, that is this continuous line. And this suppression is what we call jet quenching. This jet has interacted through the quark-gluon plasma and almost disappeared. So this, of course, has also been measured at the LHC. So here, for instance, we will have two back-to-back jets, as we will see them in calorimeters in proton-proton collisions. But when we go to heavy ion collisions, one of these jets has lost, this one here, much more energy than the other one, and as we see as the deposition of energy in the calorimeters. And this phenomenon is what we call jet quenching, and the main driver for this energy loss that the jets experience when they propagate through the quark-gluon plasma is what we call medium-induced radiation. So medium-induced radiation is nothing more than QCD Bremsstrahlung. It's like the electromagnetic Bremsstrahlung, but in QCD. So the partons that I'm showing here as springs and lines in this sketch of a jet, within a jet, interact with the quark-gluon plasma, and these interactions led them to emit gluons that I'm putting here as red springs. And these gluons most of the times end outside of the reconstructed jet, outside of the yellow cone that we reconstruct in the experiments. So basically part of the energy of the jet is lost because it's not reconstructed inside the jet cone. And this is basically the main reason why we see the jets, as we see here, suppressed in heavy ion collisions with respect to PP. And we can have even extreme cases, as what we have seen here, where we, instead of having the typical back-to-back jets that we usually observe at LHC energies in PP collisions, one of the jets is here, but the other one has completely disappeared because it has lost all its energy through the propagation of along the quark gluon plasma. And this phenomenon of this theory of medium-induced radiation is a QCD theory that allows us to compute this energy loss, has been developed. This is a little bit technical, so I'm not going to go through the details, but has been developed many years ago by these people here in the 90s. And basically the idea is that when you have a highly energetic quark or gluon that propagates through the quark gluon plasma, it's going to interact with it through scatterings that are shown here as these blue sprints. And these scatterings are going to induce radiation of gluons. And this is basically the main sketch of the main diagram for medium-induced radiation. So we can compute this cross-section, which would be the cross-section for this QCD Bremsstrahlung, accounting for these multiple scatterings, and this was done in the 90s. And by this cross-section, we can compute the probability of a quark or a gluon of losing energy in this high energy limit where the quark moves basically in this straight line. And as you can see here in the drawing, there is no, this quark doesn't move in the transverse plane, while the gluon, it gets some change in the transverse direction. And while this was developed in the 90s, it has been very difficult to numerically evaluate this formula, and happily in the last years, here in collaboration with Liliana also at LEAP, we have basically developed the state of the art of these formulas with much more accuracy. And basically I would say that if you ask for, in our community, which is the state of the art of these BDMPS formulas and which is the most accurate determination of gluon medium-induced radiation, I would say that this is these papers we develop here. With this kind of formulas, you can compute observables such as this one, which is what we call the RAA, which is nothing more than the yield of produced particles in heavy ion collisions with respect to a scale number in PP collisions. So when you go to compute these things, what would you expect? Well, the first thing is that if your particles do not have any color, they don't interact with the quark gluon plasma, so for instance, photons, they will not experience interactions with the QGP, so this RAA should be 1. And this is what we have seen here in data at the LHC by the CMS collaboration. And then when you look at particles that come from quarks and gluons, so B jets or charged hadrons, what we see is that this ratio is below 1. And this is basically due to the fact that these particles have lost energy with this phenomenon that we call jet quenching. And this basically, people have tried to describe this data with different formulas for medium-induced radiation as the one that I showed you in the previous slide. And with this kind of formulas, what you can do is try to extract transport properties of the quark gluon plasma. So you feed this data, and with this data you can extract things like Q hat, which is the average transverse momentum that a particle gets by the interactions with the quark gluon plasma. And this is a review that Liliana wrote a few years ago, where she basically summarized the current extractions of the jet transport coefficient. So we have learned a lot about energy loss and about transport coefficients, but what I was saying to you at the beginning of this talk is that what we want to learn is not only about transport coefficients. We are now in a more, let's say, precision era of heavy ion collisions. What we want to learn is about the dynamics of the quark gluon plasma at different energy scales. And for that, we need to go a little bit forward in these calculations and do things that are a little bit more sophisticated. And for instance, while I will not talk about this in the rest of the talk, I wanted just to make some advertisement because this is something that Andre, who is now at LEAP in Braga, is developing. He's trying to extend these medium-induced formulas that I told you 2 slides ago, the BDNPSD formulas, to try to make jets sensitive to the flow of the coagulum plasma as it's a liquid. It flows, and also at the temperature gradients of the coagulum plasma. And I'm sure Andre will talk about this in a few weeks. I think he's giving a seminar also here. And the idea is that in some sense, jets could be also sensitive to the flow and not only to these transport coefficients of the coagulum plasma. But what the community basically has been focusing in the last years is about jet substructure. And it's this idea that you're not only sensitive to energy loss, to this radiation that goes outside of the cone and you cannot reconstruct, but you are also the jets, the inner structure of the jet, what remains inside this cone gets modified. And gets modified because, for instance, some of these medium-induced gluons, this QCD virunstralum, can stay inside the cone, modifying the branching with respect to what I have here in black, which would be the PP branching. But also it gets modified by many other phenomena. For instance, we have here a medium response, which is the fact that if you have a jet that propagates through the coagulum plasma, these gluons that it lost, that this energy that it lost, it gets deposited in the coagulum plasma and creates a back reaction of the liquid through the propagation of the jet. And this back reaction is correlated with the propagation of the jet. So when you measure a jet in an experiment, you cannot separate what it comes from the back reaction of the medium and the jet. So basically, you don't know what is the contribution of medium response. And this kind of phenomena that are intricate and convoluted and complicated modify basically also the inner structure of the jet, because, for instance, this medium response is expected to go at large angles. So you would expect an excess of soft particles at large angles. And we can try to use these modifications of the inner structure of the jets to prove the QGP at different length scales, hopefully from the largest ones corresponding to the fluid dynamics to the shortest ones where we would expect to see these quasi-particles, that should be there. And the idea of this, of course, is not totally new. It has been something that we have developed as a community in the last maybe 5 years, maybe a little bit more. And what kind of substructure you can look at. For instance, we can look at jet shapes. So jet shapes are a variety of observables that have been measured in the LHC, both in PP and heavy ion collision, that give us information about how the energy of the jet is distributed with respect to the jet axis that is shown here as this black line. So basically what we see here in the left panel is the jet shape with respect to the distance to the jet axis. And what we see is that it has this shape here, which means that most of the energy of the charged particles within the jet are close to the axis, and then it decreases a lot when you go to larger distances from the jet axis. And when you compute the ratio of this jet shape in length with respect to PP in the bottom panel, what we see is that it's compatible with 1 for small angles, but there is an excess as large angles, which means that jets in heavy ion collisions have more energy toward the edge of the cone than jets in PP collisions. So this is a modification of the structure of the jet. And we can also go and look at jet fragmentations, which are kind of complementary to jet shapes. And instead of giving information about the transverse extraction, this gives us information about the longitudinal extractor of the jets. And here we have the ratio of the jet fragmentation in length with respect to PP, with respect to the energy of the hadrons within a jet, with respect to the with respect to the ratio of the energy of the hadrons with respect to the PP of the jet. And what we see is a big excess here and a little bit of decrease here, which is compatible with the fact that probably hadrons within the jet have lost energy, and that's why you have a shift between from hadrons with intermediate values of C to low values of C. This is compatible with energy loss. And these observables are very interesting. They give us information. So we now know that jets have more soft particles in the edge of the cone, and they have an excess of particles with low PT in heavy ions with respect to PP. But unfortunately, how to describe this data is complicated. Like, people have managed to explain this data with different physics and with different phenomena. For instance, you could try to explain this data only with medium-induced radiation, or maybe you can include medium response. So it's not easy to find out what is the quantitative description of this data and which phenomena is driving what. And this is due to the fact that these observers are giving like an average information about the jet, how the energy is distributed inside the jet. So we would like to go a little bit more differential and maybe have access to something more related to scales in the quark gluon plasma, like an angular scale. And this is something that also has been done in the recent years, and is, for instance, the study of jets, of jets using grooming. So the idea of grooming is that you have a jet and you want to get rid of the soft particles of the jet. And there are many reasons to do that. One, for instance, in my case, that I like QCD, we don't know how to deal with these soft particles in QCD. And when you have the jet, you can try to reconstruct the jet in a way that you get the two hardest subjets within the jet, which are drawn here like in this violet color, and look at the angle between the subjects and study the suppression in heavy ion collisions with respect to PP as a function of the angle between the subjects. And what we see here is that there is a strong suppression, and that this suppression increases when this angle becomes large, which means that broader jets, so jets with two subjects that are more separated, lose more energy than jets that are less broad. And this is something we have measured, but again, explaining this becomes complicated, and people have managed to explain and describe this data with different physics. And also there is a problem with this kind of observable, and is that if I look at the observable in proton-proton collisions, which is these black points we have here, and I compare it to proton-proton Monte Carlos, I don't get a good description. Here, for instance, we see that in the large angular region, which is the one that is more interesting for the physics we are looking for, there is even a factor 2 of discrepancy between some Monte Carlos and the proton-proton data. And that's not good, because as we look at our modifications with respect to PP, that is our baseline, if our baseline is not correctly described, we are not going to learn much about our observable. And the idea is to try to find observable that give us access to angular information that can be mapped maybe to some QGP scales, but that are also well described in PP. And in this kind of process of thinking, what can we do now that we have a bunch of observables measured and we know that jets get modified, but then we are not very able to really deconvolute the different physics phenomena that are driving these modifications, we came out with this idea, and it's the use of energy correlators. So this is what is basically my research about, or my recent research about, and what I will talk in the rest of the talk. These energy correlators is not really like something we came out, it's some observables that were already proposed in the 70s, but they were very largely forgotten, and what we are trying to convince, or I will try to convince you, is that they are a good idea for heavy ion physics, and maybe we can learn something about the QGP with them. So I think they have very nice properties, and it's at least worth trying to develop a formalist for energy correlators to see how successful we are in extracting the dynamics of the quark gluon plasma. So what are these energy correlators, or in short, energy correlators? Well, the idea is that correlations is something that is used in many areas of physics. In condensed matter, for instance, correlations are used in a daily basis. But when we go to particle physics, we don't use correlations much. And for instance, here what I'm showing is the cosmic microwave background, which is studied through correlations of temperature fluctuations. So the idea is, can we do something similar in collider physics? And for collider physics, the idea is to try to do correlations between energy flux. between energies, because energies is something that is very related to energy, to collider physics, and also because it's what we measure really in the experiments. So the idea is to look at correlators of this energy flux operator that has this kind of formal definition that we see here, that basically gives us just the energy in the direction n1. So you have here a direction n, and you look at the energy deposit in this solid angle here. This is what the energy flux does. And you can look at correlations between different energy flux. So for instance, if we were thinking about the one-point energy correlator, it would be just the total energies through this area element. So basically, summing the energy of the particles in a given direction that you measure in an experiment. So something very simple. But what I was saying is that we don't want to really have just an information about the energy. We want to have an angle or some information about the scales of the quark-gluon plasma. So we need to go a little bit more differential, and the first idea we have is like, oh, okay, instead of studying a one-point correlator, let's go and study a two-point correlator, which is the simplest one apart from the 1 point. And what is the two-point energy correlator? Well, it would be the correlation between the energy of the particles in these directions and the energies of the particles in these two directions. So you will have to measure all the particles in the direction n1 and all the particles in the direction n2 and look at the correlations weighted by their energies. So in that, it's like a kind of simple definition, and it can be measured in the experiments. I will show you some plots later. And theoretically, to compute this observable, you just need to compute the inclusive cross-section to produce two particles in the I and j, in the direction I and j, weighted by their energies and divided by the Hart scale of the process. So this is our observable. This is basically the simplest energy correlator we can create, but you could think about doing energy correlators with n particles. And as we are interested in angles, we are not interested in all the information that comes from these vectors n1 and n2. So we are going to integrate all the variables instead of except of this angle. So we are going to just look at the correlations as a function of the angle, which is encoded in this observable that will appear a lot of times in the rest of the talk, which is the two-point energy correlator as a function of the angle. And this observable, it's quite simple, and we think how to compute this observable in QCD. We just need, for instance, let's think about it at leading order. So we just look at the simplest case, and we say, let's compute the two-point energy correlator for a quark at leading order in QCD. So it's the cross-section for this diagram for a quark to emit a gluon, which is nothing more than this cross-section here that probably many of you recognize from the QCD splitting functions, and you then have to weight it by the energies of the particles and integrate over C. Well, you have to integrate over the energies, but I have written everything in terms of C, which is the fraction of energy of the two pairs with respect to the initial energy. So if I take this formula and multiply by C and 1 minus C and integrate over C, it's clearly that the behavior in theta is 1 over theta, because it has a 1 over theta here. So it's a very simple expression. This is the two-point energy correlator at leading order in QCD, but of course, we don't want to remain at leading order because this observable, as you can see, has divergences when theta goes to 0, so you want to resum these kind of logs that come from these divergences, and this has been done many years ago in this paper by Maldacena, and it was not done in QCD, it was done in conformal field theories. And the idea is that if you look at the two-point energy correlator at a small angle, so the separation between the particles must be small, and this is what we need because we are looking at particles inside jets, so we'd never go beyond this small angle approximation. You can prove that it can be given by this formula, that, okay, I'm not going to go through the details, but it's just a sum of operators with a given twist, which is given by this tau here. So for the ones that know a little bit more about this, if I put the twist equal to 2, I get here 1 over theta, which is what I was expecting from the leading order simple calculation. And what happens is that, okay, this is before renormalization. When you renormalize, you get something like this. And this is basically already resumming. So this would be the leading order result plus next to leading log resummation, but obtained through conformal field theory techniques. And this was done in 2018, and what we see is a very simple formula. It's something that is just a power law, given by 1 over theta to the power of 1 minus this gamma, that is the twist 2 spin 3 QCD anomalous dimension. But the important thing is that it's something simple that looks like a power law, and actually for jets, this twist 2 spin 3 anomalous dimension is close to 0, so basically this behaves like 1 over theta. But of course, this was done in conformal field theories, but QCD is not conformal. In QCD, there are scales, and even if we take that all our quarks have no masses and we can treat QCD kind of as conformal, at some point, you must break this conformal behavior, this power law behavior, because you find a scale in the problem, and this scale is lambda QCD, the scale where you end up being in a non-perturbative regime. So what we expect is that this 1 over theta behavior in black that comes from conformal QCD, conformal field theories, is breaking at some scale proportional to lambda QCD divided by the energy of our jet, at some point due to the appearance of confinement. So here we will have the perturbative regime, and here the breaking of this perturbative regime. And this is what we expect, and actually people have been looking at that during the last years, and they have looked at that in CMS data. So this is a paper done by some theorists where they take CMS open data and try and look at the 2-point energy correlator. So this is basically the same observable that I have here, but multiplied by the angle. And what we see here is that if you have 1 over theta and you multiply by the angle, you have something that is rather flat, because this gamma 3, remember, that is almost 0. So this is the region where the QCD result comes from conformal field theory, but at some point, data show that you have a transition to the non-perturbative regime where you break the conformal field theory behavior. So we see that at large angles, we have perturbative QCD, and then at very small angles, we have the non-perturbative behavior. And basically, you can relate this angle 2 times, which is nice, because this is what will happen at short times, and this is at later times. And this is already measured, well, not measured because this is open CMS data, but of course experimentalists were not that happy with this open CMS data. They want to do it properly with, you know, the unfolding and these things in a proper way, not in the way that theories we do. And they went, but they were very interested, which is nice. We convinced them that this is at least interesting, and they look at it, and they look at this these results were presented a little bit less than 1 year ago, and this was presented in heavy ion conferences, which I think is very interesting because these are measurements in PP collisions. This is the 2-point energy correlators all in PP collisions. But the measurements in PP collisions, the first measurements really done by experimenters were done by heavy ion collaborations, which I think it shows how the heavy ion community is very interested in these observables. And the measurement on the left is done by STAR, which is a collaboration at RIC, and this one is done by Alice at the LHC. And we see the same thing in the two plots. This is the 2-point energy correlator as a function of the angle, and we see the 1 over theta perturbative QCD behavior, and we see the breaking of this perturbative QCD behavior when hadronization, when the non-perturbative dynamics turns on, which is very nice. We have this preliminary data, and the idea is, can we use these observables for heavy ions? How this observable will look in heavy ions? And the question is, why is this interesting in heavy ions? And this is why we think these observables should be very useful for heavy ions. The first thing is that they give access to angles. And they give access to angles without any complicated declustering techniques, in principle even without the need of grooming. So they are simple observables that just look at the correlations of particles within the jet, giving access to angles. And then what we see here is a clear separation between perturbative and non-perturbative regimes, which is good because sometimes when we want to study observables, as the theta G that I showed you before that has a factor 2 between the Monte Carlo and the PP result, non-perturbative corrections spoil our ability to use observables to study QGP physics. So here we have something that has the non-perturbative effects separated mostly from the perturbative effects. And then in this perturbative regime, this is known at very high accuracy because the observable is simpler than other jet substructure observables. It means also that it's known at very higher accuracy. And then something that I didn't mention that I probably should have when I show the formulas for the observables is that the 2-point energy correlator or the endpoint energy correlator is defined through inclusive cross sections and weighted by the energies. But what I was showing in all these plots is this n fixed to 1. So I was waiting just for the energies of the particles. But I can increase this weight. And I can put n equal 2, for instance, and wait for the square of the energy. And this allows us to further suppress soft physics. So we can play with the ways to try to access different kind of physics. And then also, I will not have time today, but you can define many different energy correlators only using 2- and 3-point energy correlators in heavy ion collisions. So that means that gives us a very nice base with very nice properties that at least I think we should all consider as a possibility for heavy ion collisions. So the question is how this 2-point energy correlator will look like in heavy ion collisions. And we are not yet there, like we have calculations, but this is far still from what we need to compare to data. So this is just like the first developments, theoretical developments on the energy correlator approach in heavy ion physics. And the idea is that how I compute this observable in heavy ion physics. So well, the observable was the cross section weighted by the energies and divided by the Hart scale, which is the initial energy of the jet. So the energy of the jet, E, and then the energies of the particles. So if I go and I cancel these C's, basically my observable is this one. And this is what I want to compute. And this was what we have in PP. So what is the difference between proton-proton collisions and heavy ions is that to the proton-proton that I'm calling here vacuum cross-section, we have to add the contribution coming from medium-induced radiation. So we have to add the extra emissions that the jet can have due to the interactions with the quark gluon plasma. And these extra emissions are computed in this cross-section that I told you before about with the BDMPS approach, for instance. And we can write it in a way that we kind of factorize, which is not a real factorization, it's like a reparametrization of the medium-induced cross-section, such as a factor that comes with the vacuum one times a modification. And as this modification we know, and I will explain you in the next slide, that goes to 0 for very small angles, that means that we can still keep the vacuum resummation that happens at small angles, which means that if I go and I replace this formula here, I can write it like this. The vacuum part, the medium part, and the resummation, that is the 1 over theta behavior with the anomalous dimension that I had before. And that means that if I put Fmet to 0, I recover the proton-proton result, and if I have a model to compute Fmet, I can compute the 2-point energy correlator in heavy ion collisions, at least at leading order. The problem is that we don't know how to compute Fmet. And we don't know how to compute Fmet because even if I told you before that in this group with Liliana, we have the best approach or the most up-to-date approach to compute this diagram, this diagram is computing a very peculiar limit always. And it's the limit we need for energy loss. And it's the limit where this C here goes to 0 and this energy goes to infinite. And if this C goes to 0, this observable is not currently computed because you're weighting by C here. So this is not the correct limit for this observable. While this limit was very useful to do all this energy loss study, to extract Q hat, and to compute the hadron and jet suppression, is not the correct limit for this observable. So what we need to do is to compute this diagram but not imposing this limit. But of course, that's challenging. There is a reason why this has not been done in 20 years, and it's because it's difficult. So what we did in this paper is actually to use an approximation, and I'm not going to go through the details, but it's actually an approximation that was developed by some people in Santiago, including Victor Vila, who is now a postdoc here at LIP. Without going through the details, if we manage to compute this, what we would expect is that at very small angles, as Fmet goes to 0, we get the proton-proton behavior, and then at some point, we get some extra contribution coming from this approximation to this diagram. And this is basically what we see here, and is the 2-point energy correlator as a function of the angle. And what we see is that at very small angles, the result agrees with the dashed line, which is the proton-proton result, the one that has this power law behavior, this 1 over theta. And then we have an enhancement from medium-induced radiation that I have plotted here in 3 different colors, depending on the medium parameters that I put to my calculation, on the value of Q hat. And this is, of course, the first, basically, approximation to this diagram. This only accounts for medium-induced radiation. It would be interesting to see how other phenomena, such as medium response, can modify this observable. And this is extremely interesting, but unfortunately, what we did in this calculation is that assume that we know that our jet is a quark jet. And we do that because if we know that we were thinking in a process where you have a photon going back to back with the jet. So basically, by measuring the energy of the photon, you know the energy of initial energy of the jet, which enters, I have to go, I think, a little bit back, enters here in this denominator, and then you can cancel it here. But unfortunately, the first measurements are not going to come in photon tag jets because that's experimentally much more complicated. But experimentalists are measuring this in ALICE and CMS on inclusive jets. So this would be a little bit more complicated because if you don't have a photon, you don't have the initial energy of the jet. And if you don't have the initial energy of the jet, your calculation is a little bit more complicated. What time is it? What time did I start?
You have 10 minutes.
Okay. No, it was just like to know if I skip some slides. So, and this is the observable, but I told you from the beginning that our goal was to strat scales. And can we strat scales? And at least in this simple model, what we know is that at some point, medium-induced radiation has to turn on, and we can try to fit. So what we did is run this for thousands of, well, not thousands, but hundreds of different variations of the parameters, and fit this onset, fit the place where this radiation turns out. And what we see is that this agrees with what we would expect from the calculation, which means that we can try to use these observables to extract physics related to the quark-gluon plasma. And actually, this onset has a physical meaning, and is the idea that when you have a quark that emits a gluon, this emission takes some time. But if this time is very, very long, it can happen that the emission already happens outside the medium. And that means that the emission cannot be due to the medium. And this poses a maximum time for the emission to happen inside the medium, given by the length of the medium. And that turns out, if you put a maximum time here, you get a minimum angle, which is the minimum angle for medium-induced radiation to happen. And what we see is that if we fit this, indeed, we get something that behaves as the minimum angle for medium-induced radiation. So everything seems that is going in the correct direction. Still, this is a very simplified model, and we need to improve it. And just to basically show you a little bit more on what things experimentalists are doing, is that, okay, up to now we have, say, the 2-point energy correlator in PP and heavy ion collisions, but what happens if we have heavy quarks? So if you have light quarks, we can assume they are massless, that's not a problem, but if you have a boson quark, probably assuming that it's massless is not a good approximation. And what happens is that heavy quarks introduce a new scale, which is the energy of the quark. This scale is larger than the lambda QCD scale. So if we think this is the 2-point energy correlator in PP that I showed you a few slides before, and we have the power law behavior, and at some point, the confinement, the breaking to non-perturbative dynamics. So what happens if I put, instead of a massless quark, a heavy quark? Well, what I would expect is that to have a modification from this perturbative behavior at angles larger than this angle here, just because the mass of the quark is larger than lambda QCD. And indeed, this is what happens if I put the charm. I have the modification here, and if I put the bottom, I even have it at larger angles. And of course, this is a very just toy model calculation that I did to illustrate this, but of course, people have looked at this one thing, and this is what we call the death cone. And it's the idea that radiation, vacuum radiation in proton-proton collisions is reduced when you have heavy quarks with respect to massless quarks. And this has been, of course, studied in some papers here, how the 2-point energy correlator behaves with respect to the angle, and you're seeing basically the same plot that I showed you before, but unfortunately this is not in log-log scale, so it's not as easy to see that this is the 1/θ behavior you have before. And this also will be measured in PP collisions within the next the next months. And what I want to show is what happens if we look at this in heavy ions. So what you would expect probably is that we have the death cone and then the medium-induced radiation here, and indeed, you can see this. So I'm not going to go through the details, but basically the same formalism we use, you can use it for heavy quarks, just making sure that you keep track of the masses of all the particles in your calculation. And what happens is that at small angles, you have the death cone, so the green and the orange curve are the bottom and charm curves in heavy ion collisions, and the dash curve is, the dash curves are PP, and the solid curves are always the equivalent one in heavy ions. So for instance, we have here the green dash, that is PP behavior in bottom, and what we see is the death cone with respect to this behavior here that would be the light quark, which has just the power law behavior. And what we see is that in this left part, we have the death cone, this suppression with respect to the massless behavior that we already saw in PP, but at large angles, we have the medium-induced radiation. So we have two separate scales, and that means that energy correlators are allowing us to resolve two different angular scales, the one that comes from the onset of medium-induced radiation and the one that comes from the onset of the death cone. But I could think of changing, this is done for a given jet with a given energy and for a given set of medium parameters, but I can think of changing, for instance, the length on the quark gluon plasma that the jets see. And maybe if I put these scales together, like in a way that I change the length so the two angles approach each other, this medium-induced radiation can start interfering with this death cone suppression. And indeed, this is something that we see here, and is that if you start changing the parameters, you start from here, which is the same plot that I had in the previous slides, and then you change the parameters, you may end up with the medium-induced radiation moving through, to this part and filling the death cone. And for instance, here we already see that in the bottom, if you look at the green curve that is not dashed, the solid one, you don't have a death cone anymore. The death cone and the medium-induced radiation are together, and this is what we call that medium-induced radiation can fill the death cone. And this is something that was proposed many years ago, but we have not yet measured. And the idea is that maybe energy correlators are interesting to look this kind of observables because they allow us to resolve different scales, but also allows us to really see new physics coming from the fact from the fact that we cannot resolve the scales anymore for a given set of medium parameters. And well, I'm going to skip this because it's a little bit technical, and I'm just going to go to the conclusions. And I hope I convinced you that heavy ion collisions are very interesting and that there are very important questions to be answered in the next I don't know, almost 20 years of heavy ion collisions that the LHC has scheduled. And I think the biggest question to answer is how we form a liquid for quarks and gluons that are almost asymptotically free. I think one of the tools we have to study this, to try to understand how we form these liquids, is to use jets, and as jets can be used, and especially the inner stratosphere use, as a microscope of the QGP, allowing us to prove different scales within the quark-gluon plasma. And in that quest of these weakly coupled partons within the quark-gluon plasma, I think energy correlators, which are kind of new for us, but not new for conformal field theories, have great potential because they have very nice properties for jet substructure studies of the quark-gluon plasma. But of course, take this with caution because we are starting to develop this field. So there are many new theoretical developments that need to come in order to do proper comparisons to the experimental data, and experimental data at the LHC are expected already this year. So, and just to end some publicity, we have this energy correlators workshop that is the first ever energy correlator workshop that will happen in Mainz this summer. So if you're interested, just let me know because I'm one of the organizers. So thank you very much.